In this video, we are going to discuss about the basic structures for infinite impulse response systems, that is IIR systems. So what are these IIR systems? So these are the systems which are just having poles, and these poles are non-zero poles. So this is equivalent to saying that output depends on the past instances of the output, or you may say that there is a feedback mechanism. So as far as the structures are concerned, so there are variety of structures that exist, and each have its own merits and trade-offs. So by structure, what we mean is that these are the algorithms or hardware descriptive forms which result in the IIR systems discussed herein. A fundamental merit includes the computational complexity, and that is the number of constant multipliers that the algorithm would have and the number of storage registers that you would need. So ideally you would want to have a system which is less computationally costing. Moreover, very large scale integrated circuits implementation have some further constraints that includes the area of chip, how modular the system or design is. Can you separate your system into subsystems and write the code accordingly? And moreover, the simplicity in data transfer. Furthermore, some multiprocessor implications and implementations are also in place, which look into the partitioning of algorithm and some communication requirements in multiprocessor systems. And lastly, you would have to consider finite precision requirements, that is in terms of floating point and fixed point schemes, and you would be having the quantization noise that you need to minimize. So when we are designing an IIR systems, so the structures would have some requirements whether you want to reduce the complexity and you can allow certain area of a chip and you can allow a modular design. So there is going to be some trade-offs that you can tick some of these metrics while you can't other metrics. Now moving towards the direct form structures using signal flow graphs of IIR systems. So we are considering an nth order system. So this is a very generic form. And in this system, we have a type 1 form, and that type 1 form is expressed over here. So the source node is x of n and the sink node is y of n. On the left side over here, we have zeros. So in the transfer function, the zeros are in the numerator. So these are those zeros which is on the left side. So over here b0, b1, b2, b3 up to bm are the constant coefficients of the linear constant coefficient difference equation. Whereas z inverse over here and so on deals with the delay. So this x of n is now, after the delay, it's now x of n minus 1. So in between we have vn, and on the right side we have poles, and the contrasting feature over here is that there is a feedback mechanism because of these poles. Herein the constant coefficients are a1 to an. So this is a standard type 1 of a signal flow graph. Now converting this type 1 to type 2 is quite straightforward, and the only difference is that in type 2 these poles will be represented on the left side, whereas the zeros are represented on the right side. So this transition of poles from right side to the left side is made possible because of the superposition theorem of LTI systems that we are considering right now. Now that we have type 1 and type 2 systems, so let us summarize the two systems in terms of some parameters that include coefficient space, and the coefficient space for both case is n plus m plus 1. So what is this? So you can observe that the coefficients over here for zeros in both cases, they are starting from 0 to m. So this would yield an m plus 1, whereas for poles it is starting from 1 and going up till n. So that n is coming over here. So overall coefficient space is n plus m plus 1 for both over here and over here. Next is buffer space, that is storage. This space represents storage, and for that, in type 1 we have several buffer storage over here for zeros and separate buffer storage for poles, whereas in type 2 we have a combined buffer storage for both zeros and poles. So that's why in type 1 we have n plus m, that is counting all of this and this, whereas in type 2 we have a maximum of n and m. So presently we have set n equal to m for simplicity, but whichever is maximum, that would be the buffer space requirement in type 1 and type 2. Now moving on, we have additions, and for that we have to observe for each node, do we have two parts which are coming in. For example, this node has only one branch, right? Only one input, whereas this node has two inputs, one is b naught and another one is coming from the downward. So this is basically a summation block. So the overall additions that we need is these m and these n. So overall it is n plus m for both. Whereas multiplications, they are simply dependent on the coefficients, so that is b naught to bm and a1 to an. So they are being multiplied in the system, so they are basically the same, which is n plus m plus 1 for both. Now let us take one particular example of a second order system, and for that the transfer function is simply in the zeros, or in the numerator we have 1 plus 2z inverse plus z to the power minus 2, and in the denominator we have 1 minus 0.75 z inverse plus 0.125 z to the power minus 2. Now from here we can construct the type 1 form, and that is written over here. This is of the second order type 1 form. Here in the 0 section, this section is represented first, whereas the numerator part is represented to the right side. Furthermore, this is b naught, which is represented over here by this multiplier having a unity value. Then the 2 comes over here, and then the third b2 is over here, b0, b1, b2. Whereas in the numerator the signs are reversed, so this 0.75 minus would become 0.75 plus, and 0.125 is minus 0.125, and there are these delays z inverse and z inverse. Now to replicate this, so the denominator part reflecting the poles in the system would go to the left side, and the numerator part would go to the right side, and this is done in type 2. So again we have b0, b1, b2, a1 and a2. Now again the coefficient space is n plus m plus 1 as discussed before. So over here we have the space equal to 5. So these are the space requirement, that is we have a1, a2, b0, b1, b2, that constitutes to be 5. Furthermore, the buffer space requirement in type 1 over here is 1, 2, 3, 4, whereas over here we have simply 1, 2. So this 2 as compared to 4 in type 1. Number of additions remain the same. So that is 1, 2, 3, 4. And similarly over here we have 1, 2, 3 and 4. 4. Lastly, the multipliers is again 5, which is 1, 2, 3, 4, 5. Now as mentioned, we have other structures for the representation of IIR systems, and more precisely now we are discussing about the cascade form. And continuing the second order system again, which is from the previous type 1 and type 2 form, we have 1 plus 2 z inverse plus z to the power minus 2 over 1 minus 0.75 z inverse plus 0.125 z to the power minus 2. Now what we can do is we can fraction this numerator which is over here and the denominator which is over here. So by doing so we have now subsections. So this can be considered as the first subsection, and this can be considered as the second subsection. So over here in type 1 we have represented this and this in type 1 form, that is the 0 part is over here, followed by the pole part which is over here, Moreover, the zero part again is reflected over here and the pole part is represented over here. So in type 2 subsection, the poles and zeros will be interchanged and we would have less storage requirement in terms of buffer storage. So this pole would go to the left side and this zero would go to the right side. So these two are combined over here in type 2 and similarly these two are combined over here in type 2. So note that because it's an LTI system, so you can place this after this subsection, so it would not make any difference. So in this particular case, we have all real zeros and poles. So this representation was quite straightforward. Now, assuming that we have a system in which we cannot further break this down, we can't have real poles and zeros, for instance. So in that case, we can have complex poles for this structure, and only second order sections will have real coefficients. So we are intending to draw SFG, signal flow graph, with only real coefficients. So in that case, we're going to draw this part again with poles first in type 2 followed by zeros over here and then 1 over this part but in the second order form, and this is over here. Now since this is a pole type representation, so this minus 1 by 2 would change to plus 1 by 2, 1 by 3 would change to minus 1 by 3. This is A1 and this is A2. So in general discussions, moving towards the general form, so the system function that we are considering is having a linear constant coefficient difference equation based transfer function, and that is in the numerator we have bk, the constant coefficients, times z to the power minus k. This is the z transform of the input, and in the denominator we have 1 minus summation k1 to n a k z to the power minus k, and that is the z transform of the output. So in cascade form, what we can do is, as done in the examples, we can take a common, that is a common gain, and then we can break this down into multiplications, for example by factorization. And in this part or this subsection, we have real poles and real zeros. Fk is the real zero, whereas Ck is the real pole. Moreover, in the second multiplication, that is k1 to m2, we have conjugate pair zeros and conjugate pair poles. So note that this m is equivalent to m1 plus 2m2. That is this m1 plus 2m2, 2 because there is a conjugate pair expressed over here. Similarly, the n is equal to n1 plus 2n2. So as mentioned before, these are the first order factors and they have fk and ck which are real, whereas this second subsection, multiplication of these subsections, are second order factors and they have conjugate pairs of zeros and poles. So we can further simplify this in a standard second order form, and herein we have one single multiplication, that is from k equal to 1 to ns, and we have multiplied this inward. So we got b naught k, b1k z inverse, b2k z to the power minus 2 over 1 minus a1k z inverse and a2k z minus 2. Now in doing so, we have now all real coefficients in the numerator and in the denominator. So b0, b1, b2 are real. Similarly, a1, a2 are real. And this is an equivalent representation of the above equality. Herein, this ns is basically equal to n plus 1 by 2. So that is, if say n is equal to 4. So 4 plus 1 will become 5. 5 by 2 will become 2.5, and this is the floor value. So that is ns would be 2 in that case. So that is ns is the largest integer in ns plus n plus 1 by 2. Also note that SFGs can be represented in ns factorial square different pairing and ordering. So by that we mean that you can order this in any form because it's an LTI system. So which subsection would be represented first and which later, it is all correct and you can have all those such pairings. Now moving on, if we are to draw only one subsection, not the multiplication, only one subsection, so that would have this form. That is, this is the input and this is the output. Remember, this is just one subsection. And in this second order form we have coefficients which are b0, b1, b2k and a1k, a2k. Moreover, z inverse is repeated over here. So this is type 2 form of second order, one subsection in a cascade of subsections. So herein you would observe that the constant multipliers requirement is 5, 1, 2, 3, 4, 5, and the delay registers are 2 as mentioned. Now we can simplify further by extracting b naught k out of each subsection and then multiplying each of those taken out terms together, so that can be written as b naught. So this b naught is basically a multiplication of extraction of all of these b naught k's, right? And the leftover terms are over here. Over here, this b naught is the overall gain, and this is a simplified cascade form. Furthermore, this b1 tilde is equal to b1k by b naught k. So note that this cascade form is not very suitable for fixed point arithmetic, and it is more desired for the floating point arithmetic. Now let us move towards parallel form structures. And the most important thing over here is the partial fraction expansion. So before moving on towards the general form, let us again continue our example of second order system. So we'll solve this system first and then we'll discuss generic cases. So again the same system, that is 1 plus 2 z inverse plus z to the power minus 2 over 1 minus 0.75 z inverse plus 0.125 z to the power minus 2. Now, because the order of numerator is equal to the order of denominator, so we imply this division rule. So we place this over here and we start with z to the power minus 2, then 2z minus 1 plus 1, and similarly over here we have 1 by 8 z to the power minus 2. This is 1 by 8, so this is minus 3 by 4 written over here, and then lastly 1. So if we multiply this term with 8, we can remove this first z to the power minus 2 terms, and we are left with minus 7 plus 8 z inverse. So in the second equality, that is written over here, 8 plus minus 7 plus 8 z inverse over 1 minus 0.7 z inverse plus 0.125 z to the power minus 2. Now this reflects that we can have a signal flow graph in which this 8 would have a parallel path represented over here. Moreover, this second form is expressed over here in type 2, where this pole structure is apparent on the left side and the 0 is on the right side. Also note that we can further break this down into partial fraction expansion, and for that we have 8 plus 18 over 1 minus 0.5 z inverse coming from here, and then minus 25 over 1 minus 0.25 z inverse. And for that now we have only first order parallel forms, and they are expressed over here. So 8 first path, second is over here, gain of 18, and then the pole structure which is z inverse, there was a minus here, so plus 0.5, and then the gain of minus 25 over here, z inverse plus 0.25. Now let us move towards the general discussions of parallel form structures. And the most significant part is that we are using partial fraction expansion, and the transfer function is as before. So we can break this transfer function by means of partial fraction expansion, and we have a term on the left side, then in the middle, and then on the right side. So what is this term? So it's an interesting term. So previously in the example we have extracted out 8 because the order of numerator was equal to the order of denominator, so we did the division. So this is representing that, whereas in the previous example the other parts were on the right side. So more specifically, this order of n is n1 plus 2n2 because there is a conjugate pair in dk and dk conjugate. Also, if m is greater than or equal to n as in the previous example, so then this np is equal to m minus n, else this term is removed. So that is, if the order of this is less than the order of this, So this term would not be there, so you would be left with only this term. Furthermore, if AK and BK are real, so that is this is real and this is real. After the partial fraction expansion, we would have CK, AK, small ck, EK2. These would be real, whereas these conjugate pair poles DK and DK conjugate would be complex. So for simplification and removal of this conjugate in the coefficient, so we can combine these two together, and that is done over here. So we can have this term reappearing over here, whereas combining these two terms would yield k equal to 1 to ns, and then we have e naught k plus e1 k z inverse over 1 minus a1 k z inverse minus a2 z minus 2. So in this case, this a1k and a2k, they are also real, apart from e naught k and e1k, which are also real. Again, the ns is equal to n plus 1 by 2. And to discuss further, let us consider one more example here, and this is a parallel form. So we are to write the difference equation for this parallel form, and for that difference equations, so we would start with this w1 of n. So we are taking a more generic case, so rather than 1 we consider wk of n. So in this wk of n, we observe that we have an input which is coming from x of n, so this x of n is appearing over here. Furthermore, this a11 with z inverse would mean that there is an a1k wkn minus 1. Similarly, a21, so because we are considering a k here, so a2k wk of n minus 2 is coming from here, and we have already mentioned about x of n. So this k is from 1 to ns. So this is wk of n. Furthermore, over here at the output, now this is yk of n. So this is the kth branch that we are considering, and this is equal to e naught k wk of n coming from here, and e1k wk of n minus 1 coming from here. So lastly, at the output, we are basically summing all these branches, that is k0 to np ckxn minus k plus k equal to 1 to nsyKn, wherein these parts are reflecting to the region in which the numerator have equal to or higher order than the denominator, as in the example we considered 8. So these are coming from here, whereas these parts are from here.